In this lesson, we're going to go over optimization problems. Optimization problems are what many people would call word problems, where we have to minimize or maximize some unknown variable like cost or area. So the easiest way to explain an optimization problem is with an example. So let's take a look at this example, and as we go through this example, we'll take note of general guidelines that we can follow, and then we'll outline those guidelines in an upcoming slide. So here we have a manufacturer needs to construct a box having a square base that holds 100 cubic inches. We want to find the dimensions of the box that would minimize the amount of material needed to construct the box. So the first thing that you want to do when you're faced with a problem like this is, if possible, draw a picture and label variables. So we want to construct a box with a square base. Let's label the base sides as X, and we'll call the height H. So we drew a picture, we labeled unknown variables. Now we need to come up with an equation that relates the amount of material needed to construct the box to these variables. So what are some equations that relate to this box? Well, we have a volume equation, and that's going to be good to use because you notice in the problem it says the box is supposed to hold 100 cubic inches. That's a volume. So the volume of a box is length times width times height. So in this case, our length and width are both X and our height is H. So our volume is going to be X times H. And that is supposed to equal 100. So we'll set that to 100. Now the amount of material needed to construct this box, that's the surface area of the box. Now if we look at this, the surface area of the box, we have to add up the areas of the sides of this box. The area of the front of the box, right here, that's just going to be X times H. And we have 4 of those, right? So our surface area is going to be 4 times X times H. Then we have the area of the bottom and the top. Now the bottom, that has dimensions X and X. So the area of the bottom is going to be X squared, and the same for the top. So we're going to have 2X squared. And there's the surface area of our box related back to our variables X and H. Now what we want to do is this. We have to identify, what do we want to minimize? Well, the S is what we want to minimize. That's what we want to minimize. And it would be nice if we could have this S only in terms of one variable, because we know how to minimize a function of just one variable. That's what we've been studying when we find relative and absolute extrema. So how can we get rid of one of these variables? Well, if we look back to this equation up here, we see that we can write H in terms of X. Notice that H is 100 divided by X squared. So we'll take this and substitute it in place of the H right there. And then we'll get our S in terms of just one variable that we can, and then we can minimize S and find out what X value will make S a minimum. So doing that, we get 4X and then simplifying that, the X's here cancel, and we get 400 divided by X. plus 2x squared. Now, let's identify the domain of this function. Notice that x can actually take on any value from 0 all the way to infinity. If x were very close to 0, this box would be a very tall and skinny box if x were very close to 0. And if x were very large, it would be a short and very wide box. So our domain is actually all x greater than 0. So that's our domain. Now what we want to do is we want to minimize s over this domain. Now our function s is going to look something like this. And so what we want to do is we want to find where s has a minimum. Well, how do we find where a function has a minimum? Well, that's going to be where its derivative is equal to 0. So we have to find where the derivative of this function is equal to 0, and that's going to be the x value that makes s the smallest, and that's what we want to find. So all we have to do is take the derivative and set it equal to 0. So if we differentiate s, we get, remember this is 400 times x to the negative 1. Derivative of x to the negative 1 is negative 1 over x squared plus 4x. And we'll set that equal to 0 and solve this for x. Taking the 400x squared over, negative 400x squared over, we get and now just multiplying the x squared over to the left side, dividing the 4 to the right side, we end up with, and so we get x is the cube root of 100, or 100 to the 1/3 power. And that is approximately 4.64. So that's the x that makes s a minimum. Now technically you should check that this really is a minimum, because if you accidentally maximized it, that wouldn't be good. So just double checking that. Now you're not going to have to do that for every problem. I just mentioned it this one time. For all of these problems that we do, once we set our derivative equal to 0 and solve for our variable, that will be our solution. But technically we should check that this is a minimum. And notice that if we put 0 here and our location where our derivative was equal to 0 is 4.64, put that right here. And then we pick test values like 1 and 5. And if we put those into our derivative right here, if we put 1 in for x, notice we'll get negative 400 plus 4, that is a negative number. And if we put 5 into x here, we will get 20 minus 400 divided by 25, and that will be a positive number. Once again, putting the 5 in here for x, 20 minus 400 divided by 25, and that is what? That is negative 16. So you get 20 minus 16. That's a positive number. So now what this is right here, this is our sign of f of s prime. And so this means that our function s is decreasing and then increasing. And so yes, at 4.64, or the cube root of 100, that's where s will have a minimum. So we found the x value, the dimension of our base that will minimize the surface area. Now we just have to find the height h. Well, you just have to plug 100 to the 1/3 power in here for x and solve for h. So now solving for h h would be 100 divided by 100 to the 1/3 power squared. That's going to be 100 to the 2/3 power. And that is also, using our rules for exponents, this is going to be 100 to the 1 minus 2/3, and that is 1/3 as well. So we see that our height is the same as the dimensions of our base. So this is also 4.64. So there we found the dimension of our base and our height, and they actually turn out to be the same. And that makes sense if you think about it for a second. So the dimensions of a box that minimizes the amount of material needed to construct it is a square box, one in which the length, width, and height are all the same. Now let's take a look at some general guidelines that we use when we're solving these optimization problems, just taking note that we really followed those guidelines as we were doing this example. So here are the guidelines that we can follow for solving optimization problems. The first thing you want to do is draw a picture if appropriate and label all appropriate variables. Notice that we did that in the previous example when we drew our box and labeled the x and the h. The second thing you want to do is identify all given variables and all variables that need to be found. Usually there will be a single variable that has to be maximized or minimized. So in our box problem, we had the x and the h, we identified those, and then we identified the volume of the box and the surface area of the box. And the volume of the box was a fixed constant, 100, and the surface area was the variable that we wanted to minimize. Then, step 3, find a primary equation that relates the variables to be maximized or minimized to the other variables. So that's when we took our s and wrote it as a function of x and h. And we also took our volume v and wrote it as a function of x and h as well. Then step 4, you want to reduce the primary equation to a function of only one variable. This may require using other equations given in the problem setup. So remember, that's when we took the s and we got rid of the h variable that was inside of it by setting our v equation equal to 100 and solving for h in terms of x. And then we substituted into our s and we turned the s equation into just an equation with one variable. Then determine the domain of the primary equation. That's when we said that, well, x can go from 0 to infinity, and maximize or minimize the equation over the domain using the techniques previously studied. That's where we differentiated the s and set it equal to 0 and solved for x, and that gave us where s was a minimum. So you notice how we followed all of these guidelines when we did that previous problem. And these are the guidelines that you'll generally follow for all of the optimization problems that we do. So let's take a look at a few more examples. So in this example, an aluminum can needs to be constructed that can hold 150 cubic centimeters. The cost of aluminum is 3 cents per square inch for the side of the can and the bottom of the can, and 5 cents per square inch for the top of the can. We want to find the dimensions of the can that minimize the overall cost to construct the can. So the first thing we want to do is draw a picture. And we'll label the radius of the can right here, we'll call that R. And the height of the can we'll label as H. Alright. Now, looking back at the problem, we want to find the dimensions of the can that minimize the overall cost to construct the can. We're also given that the can is supposed to hold 150 cubic centimeters. So that means we want to find the volume of this can. So the volume, now the volume of a right circular cylinder like this is going to be the area of the base. Now that's going to be pi r squared. You have to remember the area of the circle. So it's going to be pi times r squared. This is the area of the base, which is the area of the circle, times the height. So that's our volume, and that's equal to 150. Now we want to minimize the cost of the can. Now the cost equation, well, let's see. The cost of aluminum is 3 cents per square inch for the side and bottom. So we need to try to figure out the area of the side of the tin can and the bottom. Well, we already know what the area of the bottom is. That's just pi r squared. So this is pi times r squared. That's the area of the bottom, and we multiply that by 3. So that's the cost of the bottom, because it's 3 cents per square centimeter, and this is the area. Now we have to add the cost of the side of the can. Well, to find out the area of the side, think of doing this. Think of taking this can and slicing it open along a seam like this and unrolling it. And when you do that, what you're going to get when you unroll it is you're going to get a rectangle, right? This is going to be the height of the can. That's the h. And the length of this rectangle is going to be the circumference going around the circle here. Right? That's going to be the length of this side right here. So what's the circumference of a circle? Well, it's pi times diameter, or 2 pi r. So the area of the side is 2 pi r h. So the cost of the side of the can is then going to be 2 pi times r times h. And we need to multiply that by 5 because, by 3, because it's 3 cents for the side as well. Now we have the cost for the top of the can. Well, the top of the can has area pi r squared just like the bottom, so it's going to be pi r squared times 5. So that's the cost for the top of the can. So what we have here is the cost for the bottom and side, and right here is the cost for the top. Now let's simplify this as we've got 8 pi r squared plus 6 pi r h. Alright, that comes from 2 times 3 here, and then pi r h. So this is our cost equation. Now, if you think back to our guidelines, we have our cost equation in terms of 2 variables. We have to get rid of one of these variables. So we'll choose to get rid of the h right here. So we have to go back to our other equation up here, and we'll use this to solve for h in terms of r. Well, dividing the pi r squared under the 150, we get that h equals and now we'll take this and put it in place of the h right there. And so our cost equation simplifies to and we can simplify this a bit, and we get and this is the function that we have to minimize. Now notice that r can go from close to 0 all the way up to infinity. If r were close to 0, this tin can would be very tall and thin. And if R were large, it would be a squat tin can, sort of like a tuna fish can. So we want to minimize this over R from 0 to infinity. So we'll take the derivative of this and we'll set the derivative equal to 0. So if we take the derivative, we get and we'll set that equal to 0 and solve for R. And that's going to be our solution for R. So solving this for R, we get that should be a square right there. Taking R squared over here, combining with this R, dividing the 16 pi over, we get that R. That's going to be R cubed is going to be 900 over 16 pi. And then solving this for R, just taking the cube root of both sides, we're going to get that R equals 900 over 16 pi to the 1/3 power, or the cube root of this. And if you evaluate that on your calculator, that's approximately 2.62, and that would be in centimeters. Now this is where your cost function has a minimum. Technically you should verify that using a number line. If you look at the sign of C prime, you don't have to do this every time you do these problems. If you 2.62, if you pick test points like 1 and 3 and you plug these numbers into the derivative, you see that when you put 1 in to the derivative, you'll get a negative number. If you put 3 in to the derivative, you will get a positive number. So that tells us that the function C is decreasing and then increasing. So yes, 2.62 is an absolute minimum over this interval. But you don't need to do that for all of these problems, because they're always going to work out where your solution is where your derivative is equal to 0 for the problems we're considering. But it is something that is good to verify. And now that we've found what R is equal to, we can now solve for H using this equation up here, and we get that H is going to be 2.62 squared, which is approximately 6.98. And there we've found the dimensions for the tin can that will minimize the cost of construction. Just one note here, when you're approximating your variables, notice how I approximated R by 2.62 and then put that in here. It's good to try to put the exact value back into any other equations. So when I evaluated 6.98, I actually put in the exact value, or at least the value accurate to about 10 or 15 decimal places that my calculator gave me, and then I approximated that to 6.98. So just be careful with rounding errors. Now let's take a look at one more example. Now here's one that you might want to try on your own. A dog kennel is to be constructed as shown. If 300 meters of fencing is available, find the dimensions which maximize the total area. So the dog kennel is to be constructed as this rectangular region, and then you have partitions running up and down made of fencing also. So try to find the dimensions. We'll label this as X and this as Y. try to pause the video here and find the dimensions x and y that maximize the total area, given that you only have 300 meters of fencing available. Now, assuming that you did that, let's go over the answer now. So the area of this enclosure is x times y, and this is what we want to maximize. Now, we're also given that we have 300 meters of fencing, so if we add up the perimeter along with the partitions, we get that the perimeter is 2x plus 1, 2, 3, 4, 5y, and that is equal to 300. So now we want to maximize the area, so we need to get rid of one of these variables, either the x or the y we want to get rid of. So let's use this equation right here to write y in terms of x and then substitute in here, and then we can maximize a. So from the perimeter equation here, we get that taking the 2x over to the other side and dividing by 5, we get that so that's what y is in terms of x. Once again, just take the 2x over, becomes negative 2x, and divide everything by 5, that number right there. 300 over 5, remember, is 60. All right, now we're going to substitute this in place of that y right there, and we get our area equals x and we'll write that as negative 2/5 x squared plus 60x. Now let's take note what the domain of this function is here. Now this step isn't completely necessary, but you'll see many calculus books include this step. So notice that x can vary from 0, in which case our enclosure is very tall and thin, where all of these partitions are included in here. So it can go from 0 all the way up to 150, in which case your partition is very long, like this. So basically x takes up both of these sides, and if we have 300 meters of fencing, that means we're going to have 150 for each of these lengths, so x can go up to 150. So we want to maximize a over this interval. So you'll see many books include this. However, the solution will still be where our derivative is equal to 0. So now, finding where this has a maximum over this interval, we're going to take the derivative and set it equal to 0. So our derivative is going to be negative 4/5 x plus 60, and setting that equal to 0, that will imply that taking the negative 4/5 x over, we're going to get, and that implies that x, multiplying both sides by 5/4, x will equal so 300 divided by 4, that is going to be 75. So this is what x should be chosen to be in order to maximize the area A. Then to find what y is, you just have to substitute 75 in here for x, and you'll get y. So then y will be negative 2/5 times 75 plus 60, and so that comes out to be 30. And so therefore, we found that x should be 75 and y should be 30. So those are the dimensions that we should build this enclosure using 300 meters of fencing in order to maximize the internal area. Now let me just mention one other thing. You'll see some books do this. Just to verify that 75 really is a maximum over this interval, remember how you determine where a maximum for a function is over a closed interval. You find where its derivative is 0 or does not exist, which is what we did, that's 75. And then you test the endpoints and those critical numbers. So just note that a of 0, if you put 0 in to a right here, you'll get 0 times 60, well that is 0. And a of 150, that is equal to 150 times, well, if you evaluate 2/5, negative 2/5 times 150, you will get negative 60 plus 60, that will be 0 as well. You can just verify that. And a of 75, that is going to be 75 times, and if you put 75 in here for x, you will get back 30 in here. So that will be 75 times 30, which is 2,250. And the units there would be square meters. So that verifies that 75 really is a maximum for a over this closed interval. But like I said, you don't really do that. All the problems that we're working on, the maximum or minimum will occur where your derivative is equal to 0 for the particular problems we're working on. And so here is our answer. Let's look at another problem. Now here we want to find the dimensions of the rectangle with the largest area that can be inscribed in the region bounded by the curve y equals 4 minus x squared and the x-axis. So down here we have the graph of 4 minus x squared. It's just a parabola with a y-intercept of 4. So what we mean by inscribing a rectangle is you want to put a rectangle in here that looks like this. And so you see, we want to choose the rectangle that has the largest area. So you see, we could pick a rectangle like this that is very long and short like that, or we could pick one like this, tall and thin. And so we want to pick the one that has the largest area. So what we're going to do is we're going to label the dimensions of this rectangle here. Now notice that point right there is on the parabola, so we'll label that point as x, y. And so also note that if the y-coordinate of this point is y, then that is the height of this rectangle. So this distance is y. And this distance will be 2x. So then the area of this rectangle, as we have it drawn, is 2x times y. And notice also that the x can vary from 0 up to 2. So the x's can go from 0 to 2. So we want to maximize this. Well, we need to get rid of one of the variables. Let's get rid of the y. So we want this equation only in one variable so we can differentiate it. So let's get rid of the y. So how can we do that? Well, this point sits on the curve y equals 4 minus x squared. So we can substitute 4 minus x squared in for the y right here. And so we'll get and now we just have to maximize this. So let's simplify it as and now we just need to differentiate this, set it equal to 0, and that will be our solution. So if we differentiate this, set it equal to 0, we're going to get that taking the 6x over to the other side. And of course we get that x is going to be 8/6. So, or of course that simplifies as 4/3. So that is the x value that will maximize the area. Now note one other thing. You can check that this is a maximum over this interval from 0 to 2. This isn't really necessary, but you'll see textbooks do it. If you want to verify that this is a maximum over this interval, you would test the endpoints and that point. So notice a of 0. If we put 0 into our area function here, we're going to get back 0 times 4. Well, that is 0. A of 2, the other endpoint, that is going to be 4 times 4 minus 4, which is 0 also. And a of 4/3, putting 4/3 in here, you're going to get 2 times 4/3, so that's 8/3, times 4 minus 16/9. And so let's write that as, and that of course simplifies out to 160/27. I used my calculator there to do that one. And so that's approximately 5.9. But the fact is that that is bigger than 0, so that's where our area has its maximum. So we found our x-coordinate. To find the y-coordinate, just plug 4/3 back in here for x. So we found that x is 4/3, y is 4 minus 4/3 squared. That's just going to be 16/9. And so we're looking at 36/9 minus 16/9, so we're looking at 20/9. And so the dimensions of our rectangle would actually be 8/3. Notice that this distance is twice x, right? Because the distance from here to here is x, because that's the x-coordinate of this point. So the total distance is 2x, so 8/3 by 20/9. So that's the dimension of our rectangle, 8/3 by 20/9. And that's the answer to our problem.